at truss. Basically, we know what we mean by truss. Truss is a structure in which the structure composed of slender members. Okay, and these connections may be by bolting, by riveting, or by welding. And another another aspect is another aspect, or we can say a gusset plate. We can say a terminology. The gusset plate is a common plate to which different members or two or more members are connected by using bolting, riveting, or welding, whatever is the connection. Okay, so basically, in a broad way, if we think about classification, so there are basically two types of trusses. First we can say roof truss, and second we can say breech truss. Means first, uh, one truss we can say which is used in the construction of our buildings, say commercial building, residential buildings, or any types of we can say commercial yards, we can say. And a second type of truss we can say a breech type of truss, which can be used in transportation point of view. Okay, so in breech truss, regard to breech truss, that truss may be constructed for we can say for roadways, for another we can say for railways, etc. Okay, there are some basic assumptions in the analysis of truss, we can say. So there are three basic assumptions. They are: members are pin jointed. All the members connected in the truss are considered to be pin jointed. Okay, loading is applied only at joints. No loading is allowed at the center or anywhere in the member. Only loading is applied at the joints only. Then self weight of a member is neglected. Okay, self weight consider nahi ki. We will not consider self weight of a member during analysis. Okay, so basically these three assumptions taken together to solve any truss. Now, method of analysis. Method of analysis, for the truss, there are two basic method of analysis for the truss: method of joints and method of sections. Okay, so method of joints, if we think about method of joints, this method is very simple, in which various joints in the given truss are considered to be analyzed for a complete analysis of a given truss. Okay, then method of section. If we say method of section, so one section is applied for a given truss, and say we can say a left or right side of a part of that section we have to analyze, and we have to analyze the whole truss. Okay, now next is a numerical problem. This numerical problem we will consider, we will solve this numerical problem with the help of method of joints. Okay, so the question is the calculate member forces in BC for the truss shown below by method of joints. Okay, so this is a truss, we can say, and this truss, in this truss, we can say these are the number of joints. This is 1, 2, 3, 4, 5, and 6. There are 6 joints in a truss. Okay, and at joint B, and notations are A, B, C, D, E, and F. And at joint B, there is a horizontal force of 3 kilonewton. Okay, and else at joint C, D, E, F, and A, there are no forces. Okay, basically at joint A, if we think about supports, so at joint A there is a roller support, okay, which can be moved in the horizontal direction but not in the vertical direction. It is restricted in the vertical direction movement. It is only movable in the horizontal direction. Then at joint E there is a hinge support, means this restriction, there is a restriction in the vertical direction. Rotation is possible, but this restriction, this is not movement. So horizontal movement is not possible, vertical movement is not possible, only rotation is possible. Okay, so now if we think about this truss, we have to analyze this truss for a member BC. We have to find the member force in this member BC. Okay, so first of all, step 1 will be to calculate the support reaction at joint A and support reaction at joint E. See, support reactions, again reactions, when reactions will come into picture, when there is a restriction in any direction of movement, there will be a reaction. Okay, here is a roller support which can be moved in the horizontal direction, but it cannot be moved in the vertical direction. So there will be a reaction in the vertical direction. And here Here hinge support means that vertical movement is not possible, horizontal movement is not possible, means here we have two reactions, that is in vertical direction as well as in the horizontal direction. Okay, here only one reaction because horizontal movement is possible, vertical movement is not possible. That's why here only one vertical reaction, no horizontal reaction is there. Horizontal movement is possible. Okay, next. So here if we think about this stress, we have this horizontal force of 3 kilonewton at joint B, and one vertical reaction at joint A, and two reactions at joint E, one vertical and one horizontal as a hinge support. Okay, so apply. Basically, if we have a truss, basically we have two equilibrium equations. That is summation of Fi equal to 0 means summation of all the forces in the vertical direction is 0, and summation of Fx is equal to 0 means summation of all the forces in horizontal direction is 0. Okay, but we have many a times we can see by using these two equilibrium equation we can't calculate these three unknowns, because we have two equations of equilibrium and we have three unknowns. This is 1, 2 and 3. So basically we have three unknowns and two uh, equilibrium equations, so it can be possible. So that's why one additional equation is needed. So we can calculate, we can take moment about any support which is equal to 0. We can using this another equilibrium equation, or we can say another compatibility equation. So we can solve this truss, or we can calculate these reactions. Okay, so first of all, summation of all the vertical forces equal to 0. So summation of all the vertical forces equal to 0. See, no vertical forces are there, only vertical reactions are there. So Va plus Ve, this Va direction is vertical upwards and Ve is direction vertical upwards. So vertical forces with upward direction we can take as positive, and vertical forces in the downward direction we can take it as negative. Okay, so these Va and Ve, these both the forces are heading towards vertically upward direction, so we will take as positive. So all the forces in the vertical means Fp is equal to 0. This is the first equilibrium equation. So that's why that is Va plus Ve equal to 0. Okay. Then another, summation of all the forces in the horizontal direction is equal to 0. So summation Fh is equal to 0. So ultimately we have this He means in this direction, horizontal direction, we can say this 3 kilonewton force is acting horizontally towards the right, and this He is the reaction, it is horizontal again and towards the left side. Okay, so again we can say this horizontal force towards right we can take as positive, and this horizontal force on the left hand side we can take it as negative. Okay, so by considering this equilibrium equation, the equation will be, so this is 3 kilonewton acting towards right hand side, to we can say it positive. So 3 is positive, so say we can say plus 3, whereas this He is horizontal reaction plus heading towards left hand side, so it is taken as negative. So negative He, so He, so equal to 0. Okay, so by simplifying this we can say He is equal to 3 kilonewton force. Okay, so one of the three reactions He, this reaction is determined. So He is equal to 3 kilonewton, positive 3 kilonewton. Okay, now we have these two equations, summation of vertical forces and summation of horizontal forces equal to 0, but we have these two unknowns again. We have this He, it is a known reaction, but we have again these two unknown reactions. Now this over these two equilibrium equation, we needed one more additional equilibrium equation to solve this equation, or to solve these two unknowns. Okay, so for the timing, we can consider summation of moment at a joint equal to 0. So summation of moment at a joint A is 0. So by doing this, so summation of moment at this joint A will be equal to 0. So whatever is the force applied over this, about this joint A will be equal to 0. We can equate it to 0. So if we consider joint A, then VA will not come into picture. If I consider this joint A, again HE will not be in the picture. Why? See, if I consider joint A, the line of action of VA is the same passing through this joint, and line of action of this HE is same passing through this joint A. Okay. Now, if we think about moment, so moment is nothing but so force into perpendicular say distance. Okay. Now, if we think about force into perpendicular distance for a moment, so if we consider this VA, now force into perpendicular distance, if I consider this joint and this reaction VA, so VA into what? So VA into perpendicular distance. So perpendicular distance is not present. Perpendicular distance is 0. So ultimately this force will be 0. Ultimately this force will be neglected. Okay. Similarly, HE line of action is same with this joint A. So again, if I consider this force, so HE into perpendicular distance, there is no perpendicular distance because the line of action of this joint as well as line of action for this force is same or lie in the same plane. So so perpendicular distance is again 0 in case of HE. So we can say for this force it is not possible. Okay. So what forces are possible? So this for the joint A, this 3 kilonewton is possible. Okay. And this VE is possible. Again, moment is nothing but the force into perpendicular distance. So this 3 kilonewtons into this 3. So this force is horizontal and this joint is A, and whatever distance between this joint and this application of this force is 3 meters. So perpendicular distance is 3 meters. So it is possible. So again, we can say, so 3 into this perpendicular distance is 3. So it is that. Okay. Now, secondly, if we think about this, now we have only think about magnitude. Okay. Now, first of all, think about only the magnitude. Then we think about the sign directions. Okay. Now, another force is this reaction VE. This VE again VE. If I take VE about this joint joint A, then perpendicular distance will be 6. So this 3 meter and this 3 meter will be 6. Okay. So another parameter will be VE into 6, we can say. Okay. Now whatever is the sign, and again equal to 0. Okay. Now think about the signs. Now if we think about the signs, we can take as, if I take as clockwise, if I take as clockwise as positive, and if I take anti-clockwise as negative, means all the moment about any joint which are clockwise we can take as positive, and all the moments about any point moving anti-clockwise direction we can take it as negative. Okay. If we think about this 3 kilonewton force, so this 3 kilonewton force acting about this joint A, so this force acting about joint A means this is movement according to our clockwise direction, so we can say this is positive. Again, this VE acting about this means this force is acting in this direction, so we can say this is an anti-clockwise direction. So anti-clockwise direction we can take as negative, so this force will be VE will be negative. Okay. So this is the final equation which is equating to 0. So we have taken a summation of moment about A equal to 0. So on simplification we have VE is equal to 1.5 kilonewton. Okay. Now, after simplification, we have this value VE is equal to 1.5 kilonewton. This is positive value. Okay. Now substitute this value in this equation. So we have VA plus VE equal to 0. So VA plus 1.5 equal to 0. So ultimately we have VA is equal to minus 1.5 kilonewton. Okay. So by doing this means by taking this 1, this is 2, and this is 3. So by taking these 3 equilibrium equations we can solve for these 3 basic unknowns. So these 3 basic unknowns are known. Okay. Now second step, if we are thinking regarding the joints. Okay, so we have to analyze this given truss with the help of number of joints. But from which joint we can start? Joint A, joint E, joint D, or joint B, or remaining two joints. What for what joint we can go? Okay, that we don't know. But we think about uh, one basic criteria that if I have to analyze a truss by a method of joint, I have to choose such a joint where two basic unknowns are available only. Not more than two basic unknowns are available. Okay, if I consider this joint A, there are three there are more than two unknowns are available. Basically, if I think about this joint A here, so see, this AB means we have to find the forces, all the forces. We have to find what was the question. We have the question that we have to find the member force. We have to find the member force in BC. Ultimately we have to find member force in AB, BC, CD, DE, like that. Okay, means all the member have some forces, some members have zero forces or null forces, we can say. But we have to find it. We have to find it that those forces that have that have the values, and those forces that have zero value in that. Okay, so for that scenario we have we have to consider a number of joints. But what will be the first joint? If I consider this joint A, means if we think about member force, means this is the first basic unknown, this will be the second basic unknown, and this will be the third basic unknown. Means more than these two basic unknowns are here. Okay, if we consider joint E, the similar picture, because this is a symmetrical truss. It is symmetrical about CF, we can say CF member. So again, it will be one, two, three, will be three basic unknowns. So we can't solve, and one only one known variable, that is VA we have, that is 1 - 1.5 kilonewton. But with the help of VA, we can't find these three basic unknowns. Again, with the help of these two known forces, we can't find these three basic unknowns. Okay, so we have to consider that joint where only two or less than two or two basic unknowns are available. So we can consider this joint B, we can consider this joint C, we can't consider joint C again. Okay, so at initial stage we can't consider joint A, we can't consider joint E, and we can't consider joint C. Okay, also we can't consider joint F also, because we have at present three basic unknown forces, 1, 2, and 3. Okay, so we have only choice that we have to consider joint B or we have to consider joint D. Okay, so next, so consider, so we have to consider, say we can consider joint D. Okay, so first of all we can consider joint D. So joint D will at joint D C. So at joint D, if we consider member forces, so there are two members are connected. So CD. So according to joint D, we can say DC and DE. There are two basic forces are connected. Okay, so force in the member DC and force in the member DE we have to find. Okay, but we can say we can see at joint D there will be no additional forces is applied, means no vertical, no horizontal forces is applied additionally. Okay, so just like at joint B, there is an additional force 3 kilonewton is applied. Okay, whereas at joint D there is no additional such a force is applied. So we have only these two basic unknown, that is FDC and FDE. Okay, so we will apply two basic and basic equilibrium equations. Summation of all the forces in horizontal direction equal to 0, and summation of forces in vertical direction is 0. Okay, so first of all apply summation of vertical direction. Summation of all the forces in vertical direction equal to 0. So apply. So by applying this we can say FDE equal to 0 straight away. Okay, so though as there are no forces, additional forces are there at joint D, so simply FD equal to 0. And if I consider all the forces in the horizontal direction equal to 0, simply FDC is equal to 0. See, means by analyzing this we can say this FDC will be with a zero member and FDE will be the zero member. Okay. Now, secondly, we have only two choices that we have to consider about this joint B and we have to consider about this joint D. So first of all, we have considered joint D. Now, secondly, we have only the choice that we have to consider joint B. Okay. So secondly, we will consider about joint B. So at joint B, there are two member forces, that is BC and BA. Okay. So we have to find the member forces in BC, that is FBC, and member forces in BA, that is FBA, with one additional horizontal force of 3 kilonewton acting at joint B. Okay, so simply draw a FBD. This is at joint D. Again, it is whatever diagrammatic view is here available here, it is called as FBD. FBD is nothing but the particular at a particular joint, whatever number of reactions or number of unknown forces are present, that we have to draw joint wise separately. Okay, so for that, for the joint D, we have considered only these two because there are two only basic unknowns are available. So joint at joint D, only two unknown member forces are available. So we have drawn that two basic unknown forces. Okay. Similarly, at B, so FBD of this free body diagram of joint B, we consider this. So at joint B, there will be one horizontal force of 3 kilonewton as shown in the figure, and one unknown force, unknown member force, we can say FBC, and one vertical unknown force, we can say FBA. Okay. Now another aspect is that, see, during consider this member forces, all the time we will consider about this arrow. Okay, so all the time we will consider about this arrow is far moving farther from this joint. Okay, all the time we will considering about this. Okay, if we consider, if means basically we have to consider this that arrow is moving farther away from this joint all the case. Okay, for this joint, for this joint D, it is considered as farther it is member forces is moving farther away from this joint. Again, at joint B, unknown member forces, for the unknown member forces, these are moving away from this joint. Okay, whereas this 3 kilonewton force is acting on the joint, means toward the joint, because it is given in the figure, it is given in the problem figure that 3 kilonewton force is acting toward the joint, whereas for the unknown member forces, we have to consider this basically, or we can say at initial stage, we can say this member force or the member forces are heading away from this joint. Okay, if after considering this orientation, we can say, after considering this orientation means that whatever force is you considered, it is acting away from this joint B. Now, if after calculation of FBC, we can say, okay, after calculation of FBC, if FBC value comes out to be positive, if FBC value, whatever is it is XYZ kilonewton force, what will be the value of this FBC? If this FBC value comes after this analysis, means what kind of analysis? After application of this after application of this equilibrium equations, that is summation of all the horizontal forces, vertical forces equal to 0. After application of this equilibrium equation and after solving this, if I found this FBC force is positive value, okay, in that case we will consider this assumed direction of this force is okay. Okay, means actually this whatever is the assumed direction, it is okay, it is true, that is member force is again moving outward direction. Okay, if this after calculation, if this FBC value comes negative, okay, means it shows that whatever is the assumed direction for that force, it is false. Okay, so in that case we have to assume that member force is not like this member force will be like this. Okay, so this member force will not moving apart from this joint B, whereas that for after this force is, if I found this force is negative, then we can say this force is acting towards the joint B, means In that case, if I found this force is negative, then we can say this force will actually acting towards the joint B. Okay, but at initial stage we have to consider further away position or further away orientation. Okay, so for this uh, for this joint B, FBD of joint B, we have to analyze or we have to calculate these two member forces. Okay, so joint for this we will apply the equilibrium equations. So first of all, in the vertical direction, so after application of this vertical direction equilibrium equation, so FBA, we can say we can see FBA in the vertical direction only one force is there. So only one force is there. After that, only one after one force is there is no additional force in the vertical direction, so straight away FBA is equal to 0. Again FBA it will be the zero member, so FBA will be the zero member. Okay, so then FH, horizontal force, so horizontal force is equal to 0, so all the forces in horizontal direction equal to 0. So assumed direction was FBC, so FBC. Okay, FBC again it is moving towards right, so we have already considered towards right movement is positive, so positive FBC. And again this 3 kilonewton again moving towards the right, so again positive 3 kilonewton. So in this in the horizontal direction these two basic parameters are there which can be equal to 0. Okay, so by doing this we can say FBC is equal to minus 3 kilonewton. Okay, again the scenario comes that if this negative sign comes, means assumed direction of BC is false. Okay, so actually this member force in FBC is moving towards the joint B. Okay, so by doing this by considering joint D and by considering joint B, we have calculated number of member reactions, number of member forces. Okay, so our question was we have to find the member forces in BC. So ultimately we have this member force BC, so ultimately we have to find member force in BC. So FBC is 3 kilonewton. So this is our final answer. Okay, so like that, if a question asked about calculate member forces in all the members, so consider a joint. First of consider means for the particular truss, consider the joint D, then joint B. After calculation of this, after calculation, we can say this force is zero force, this force is zero, this member is zero forces. Okay, so ultimately, if I consider now joint A, so ultimately this is a known force. First of all, at the initial stage, I don't I didn't know the nature of force in the member AB, but at present I know that member force in AB is 0. So ultimately, the at joint A there will be only two unknown forces, that is this FAC and FAF. Okay, so at present I can solve this. Okay, at present I can solve this. At present I can solve from joint E. So like that, we have to consider number of joints and we have to consider we have to solve for number of member forces. Okay, so in this it is a simple small numerical, it is a first numerical, that's why I have considered only the two number of joints. I have analyzed two number of joints and shown the one thorough representation that how we can solve this particular truss. Okay, if question ask about to calculate number of forces, all the member forces and all the members, so basically we have to consider first joint. uh, the procedure where what procedure is simple. The procedure is first of all calculate member reactions, support reactions, then consider that joint where only minimum two unknown forces are meeting. Okay, after after doing this, after knowing the member forces, another joint can be considered. Okay, so by doing this we have calculated this solution for this numerical. Okay, next. So in this we have not considered the analysis of truss by using section method. In the next lecture, we can say I can continue with the method of sections. Okay, so in this it is a analysis of, it is a very first, we can say, lecture on analysis of truss. So we have considered very basic numerical, a small numerical with a method of joint. So basically method of joint is a very simplest method to analyze. So that's why I have considered this method of joint method, and calculated this support reaction for a particular truss, as well as the member forces which have asked in the numerical problem. Okay, so next is arches and cables. So think about arches and cable. What is arches and what is a cable? Okay, now think about arches. What do you feel with arches, and what do you feel with cables? Cables are what and arches are what? Arches, if we think about cables, so where we can see a cables, and if I think about arches, so where in the picture, or we in pictorial representation, where we can see the arches. Okay, so introduction is that, so cables, the cables are structural elements that resist loads by axial tension. Okay, see, cables, 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 cables are pulled by two supports, we can say. So it is ultimately, it is a tension. If it is one thread is pulled by two hands, so ultimately that thread will be under tension. Okay, because these two hands is pulling this thread. Okay, so like cables are like thread, we can say. Our cables are, we can say thread is a prototype of cable, actual cable. Okay, and a thread is simply pull the thread. It is where we can say, in thread there will be a tension, there will not a compression. Okay, so all the forces are coming on the cables are resisted by that axial tension. Okay, all the vertical forces or all the gravity forces which are coming on that cables, that are resisted by this axial tension, not a compression. Okay, see, arches and cables, if we think about both the parameter, there are only two possibility, that one member will consider about compression and one member will consider about tension. Okay, but if we think about cables, so it is, again, it is supported by two ends. Okay, ultimately if it is supported by two ends with a sag in it, in if sag is present, so there will not be any compression. Okay, all the forces, all the vertical or all the gravity forces will be considered will be with the help of that axial tension in that. Okay, so during analysis we considered that cable is flexible and inextensible. Okay, inextensible means that whatever length is considered, 3 meter, 4 meter, 5 meter, 10 meter, whatever length is considered for that particular cable, that length will be same after application of load. Means before application of load and after application of load, the length will be same. There will be no change in the length. That mean by inextensible cable is considered. Okay, and cable is considered as a flexible member. Okay, not a rigid member, it is a flexible member considered. Then during analysis, self weight of the cable is neglected. Okay, self weight of the member is neglected. Only externally applied force, externally applied loads are considered during that analysis. Okay, now basically these, we can say, these are the assumption during the analysis of any cable. Okay, now if we think about arch, now if we think about cable, so cable, it is supported by two, we can say, a thread, we can say supported by two hands. A simple sag is there in that. Okay, and on that sag a vertical number of vertical forces or gravity forces are supported. Okay, whereas arch, arch is considered like this, we can consider like this. Okay, and when we consider about arch, now arch is not, in the arch there will be, there is no sag. Okay, we can say it is an inversion of cable, we can say. If cables are if in case of cables, unknown forces or applied loads is registered by axial tension. So in the arches, if it is an inversion of cable, so arch will be any member. Okay, So that is supported or resist, or who can resist the number of additional forces or gravity forces by the action of compression. Okay. So arch in a curved beam. Okay, arch in a curved beam, we can say in a scientifically language, arch in a curved beam in which movement at the support is fully or partially prevented. Okay, means movement at the supports is partially or completely restricted. Okay, and horizontal thrust is present at the support because it is the inversion of cable. So horizontal thrust is induced at the support. Okay, now, analysis of cables, we can say. So basic assumption we have seen earlier again, but we will see again. Only axial tension carried by cable. Okay, it is inextensible, that is length is constant. Assumed to be rigid body during analysis. Though it is a flexible member, we have considered this is a cable is a flexible member. This is a flexible member, but we can say if we consider cables means these two supports and this will be a cable. Okay, and these vertical loads, whatever vertical or horizontal vertical gravity loads is applied on this. Okay, so this will be under tension, means this is pulling towards this and this is pulling towards this, so it will be in tension. Okay, this will be in under tension. So cable, though this cable is flexible, means after doing this, means if I apply these two supports and if I lay this cable in between these two support, ultimately though this is a horizontal, though this is a horizontal layout, but there will be a sag, there will be some sag. Okay, so we can say for why this sag is there, because of this flexibility. So cable is flexible in nature, but during this analysis we consider that it is a rigid body. Okay, so for moving load it is considered as a UDL, uniformly distributed load. For the moving load it is considered as a UDL. Okay, then during the analysis cable is assumed to be perfectly flexible and inextensible. Okay, see, this rigid body and this flexible body, don't confuse in between these two terms. Okay, rigid body, we can say if these are two support and in between this there is cable. Okay, means whatever is the media, or we can say this support and this support, this can't be movable. Okay, so in this case this is a fixed support and this is a fixed support, and in between these two support there is a cable, means whole assembly it is rigid. Okay, but whereas in between these two support this nature of cable is flexible. Okay, so nature of cable will be flexible, means temperature effect is there, application of load is there. Okay, so during the rise in temperature, this sag will go on increasing. Okay, during the winter season, or when the temperature is very low, or we can say minus degree is there, minus temperature is there, so we can say this flexibility of this cable will be somewhat lower down, or we can say the as compared to high degree temperature, the at lower temperature this is somewhat rigid in case of we, if we think about flexibility. Okay, so like that. So whole assembly is rigid, but the nature of this cable is flexible. Okay, now arches. Now arches, in arches we can say, see, if this is a beam, this is a, sorry, column, and this is a beam. Okay, so this is a beam and this is the application of forces. These are the application of forces. Now uh, these are the, this is the support, we can say this is the ground level, we can say. Okay, over this these are the columns and this is the beam. Okay, now in case of a normal beam, normal horizontal beam, these applied loads are counteracted with the help of these, counteracted with the help of this internal bending moment and shear forces. Okay, in the normal horizontal beams, we can say, in the normal horizontal beams we can say these application of loads, external loads, these are the external loads are nullified or resisted by these internal bending moment or shear forces developed in between these this horizontal beam. Okay, now arching beam reduces the moment at any section due to horizontal thrust. arching beam resisted. Now arch is what? If this is a support, this is a support, and this will be your arch. Okay, so there will not any bending moment or shear force develop in this assembly. Okay, here only this distance, it is governing by only this distance, and whatever is load is coming over this arch, it is registered by this horizontal distance. Okay, again, if we think about this support, so support, this may be fixed support, this may be fixed support, one fixed support and one may be roller support, means we it can be movable, means after application of load, this roller support will move in the horizontal direction and counteract this application of load vertically towards the foundation. Okay, in any case we can say both the supports are fixed. In any case both the supports are in fixed. Okay, these, we can say this is the rise of this arch. Okay, in support, and this will this is we can say it is denoted by h, we can say the elevation of this arch from the ground level. Okay, we can say. So in the arching beam, so this is a normal horizontal beam and this will be the arching beam. So in arching beam we can say this, whatever is the load coming over this arching beam, it is registered by horizontal thrust only. Okay, so we can simply define as the structure that resists. So arch is a structure that resists applied load by the action of normal thrust only. Okay, so arch we can say, we can define as a structure that resists applied load by the action of normal thrust only. No application of, or no acting internal bending moment, no shear force is there. It is present only in horizontal beams. Okay, internal bending means whatever is the media available in horizontal beam to resist these external forces are internal bending moment and shear forces. Whereas for arches there will be the resisting media as only the horizontal thrust. By this horizontal thrust we have only this resisting media for arches. Okay, so again, if if it is a conversion of cable, so this is, we can say this is under compression because this vertical or gravity load is coming from the top over this arch, we can say, and this will try to push that arch in the downward direction. So again, this whole arch will be under compression. So whole arch will be under compression. Okay, so that's why in the first slide we can say these cables are the structural members which resist the loads by axial tension, because the nature of this cable is like this. Okay, again, after application of force, this force will try to push this cable in the downward direction. So again, this is fixed at joint, this is fixed at support, this is fixed at support. So ultimately again, after application of this load, this whole, the nature of this cable will be tensile. Okay, no picture of compression is there. Okay, whereas in case of this arches, this inversion of cable, so it is a invert of cable, so there will be only compression, no tension is there. Okay, this is fixed at this support, this is fixed at this support, and whatever load is coming, this is tried to push this arch in the downward direction. So again, this will try to settle in the downward direction. Okay, whereas this support this support will try to push this arch in the vertical direction. Again, this support will try to push the arch in the vertical direction. So again, this support will apply reaction at this joint. Again, the support will apply the reaction at this joint, means whole member, means this assembly will be under compression. Okay, so ultimately remember that cables are always in tensile in nature, as whereas arches always are in compression in nature. Okay, these are both are uh, opposite to each other, nature wise opposite to each other. Okay, now if we think about arch, if we think about arch, so there are basically, we can say, two types of arches, so funicular arch and a parabolic arch. Okay, so funicular arch, just like funnel, we can say we know this funnel. Okay, so funnel is like this top opening is very larger as compared to this bottom opening. Okay, just like means if we think we now this is a linear variation, means this is a linear variation. If we think about this linear variation into a parabolic or in a curvature in a curve nature, so this can we can say that this will be the curvature nature of this funicular shape. Okay, so just like this, so that just like this, so any arch just like a funnel which is funicular arch. Okay, another arch will be this arch means this means horizontal thrust or horizontal value in between these two supports are very large, we can say, as compared to this funnel. So this comes under the category of parabolic arch. Okay, so this is a funicular arch. Again, these are the external loads acting on this funicular arch. So in again, this is the inverse of a cable. The supporting gravity load by the action of axial compression. See, this is the axial compression because this is a support, we can say this is the hinge support. Okay, so again hinge support, at hinge support two reactions are there. So one vertical reaction, one horizontal reaction. Again this hinge support, one vertical reaction, one horizontal reaction is there. Means that what this suggests, this at this joint no vertical no horizontal movement is possible, only rotation is possible. Okay, no vertical no horizontal uh, displacement is possible, only rotation possible. But whereas these forces, all these forces are vertical direction, so no rotation as such possible practically. Only bottom only this movement is possible or displacement in the downward direction is possible. Okay, whereas this downward displacement is resisted by this reaction at the support, two supports. So that again this force will try to push or try to displace that funicular arch in the downward direction. But whereas this support will try to push this funicular arch in the upward direction, so ultimately it is under compression. So ultimately whatever these are the forces are moving through this arch. So ultimately this arch is it is completely in compression in nature. So again no bending moment, again no bending moment and shear forces occur in this arch. Okay, so again again, so only these two forces, only the axial compression is there, no bending moment, no shear forces acting. Okay, now another type, it is a parabolic arch, that is two hinge parabolic arch and three hinge parabolic arch. Okay, so in case of determinacy and indeterminacy, if we think about this, so there are some parameter regarding two hinge parabolic arch and three hinge parabolic arch. Okay, so it is see, indeterminacy is discussed in the previous presentation, my previous present in my previous presentation. We have discussed about determinacy and indeterminacy of our beam frames. Okay, so in that you can refer that determinacy as well as indeterminacy for the particular structure. Okay, now if we think about three hinge, now for the timing we will consider about 3-hinge parabolic arch, and I will give some standard formulation for 2-hinge parabolic arch. Okay, now if we think about 3-hinge parabolic arch, now 3-hinge parabolic arch are like, see, 2 hinge at this support, 2 hinge at this support A and C will be 2 hinges, and at support B will be another hinge. Okay, now this at support B will be another hinge is like that. This another hinge at B will be at this position, means at the center of this whole assembly, or we can say at this or at this or at this or at this, where at anywhere this hinge will occur. Okay, so this is the first hinge, this is the second hinge, and this is the third hinge. Okay, so ultimately this is a parabolic arch, an arch hinge at both supports and additional hinge anywhere in the rib. This is called as rib. Okay, this is called as rib, and third hinge is anywhere in the rib. Okay, and main and most importantly, this is a statically determinate structure. This is a statically determinate structure, whereas this is a indeterminate structure. Means two hinge parabolic arch is an indeterminate structure, whereas three hinge parabolic arch is a determinate statically determinate structure. Okay, so in case of two hinge arch, only these two hinges are there. Only these two hinges are there, and this third hinge is absent. Okay, so whereas why it is statically indeterminate structure, two hinge parabolic arch. See, this is a hinge support. This is a hinge support. Again, these are joint A will consist of two reactions. Joint C will consist of two reactions. Okay, number of unknown reactions are four. Okay, whereas number of equilibrium equations are three. So number of equilibrium equations are three, unknown forces are four. So to 1 degree it is an indeterminate. Okay, whereas these one number is neutralized by this internal hinge, this in three hinge parabolic arch. So that's why in the three hinge parabolic arch the number of unknowns will be three and support reactions are will be three, or we can say this number of unknown forces will be three and equilibrium equations will be three. So it is nullified with the help of this internal hinge. That's why this three hinge parabolic arch is a determinate structure, statically determinate structure, whereas these two hinge parabolic arch it's a statically indeterminate structure. Okay, so that is the basic difference between two. So this is a standard formulation for two hinge parabolic arch. Okay, so this is the standard formulation. Means if uh, 2-inch parabolic arch with UDL over the whole span, if it is given, so it is calculated by H is equal to this formula. So H is equal to this formula WL square by 8H. Okay, now H is again nothing but this rise. H is nothing but, sorry, this rise. Okay, and this is the horizontal thrust L. Okay, so this is calculated by using this is the standard formulation, that is it is calculated by WL square by 8H. Okay, then UDL over left span means half span UDL. Okay, then it is calculated by that formula WL square by 16H. Then concentrated load at crown. At crown means at what is at this point will be a concentrated load. So in that case, so H will be calculated by using this. So horizontal thrust will be calculated by using this formula. Again, all these parameters are calculation of horizontal thrust only. Okay, so all these parameters are because in the basic beam problem we have considered shear force and bending moment, because all the external force is resisted by shear force and bending moment value. Whereas in case of arches, where whatever it is 2-inch arch, 3-inch arch, it is simply resisted by horizontal thrust only. Okay, so that's why we have only calculated in case of beam we have calculated about shear force and bending moment. Okay, so here only we can calculate, or we have calculated only the horizontal thrust only. Okay, so there are the different we can say load conditions, and under that load condition different standard formulation for the calculation of horizontal thrust for that particular arch, for 2-inch parabolic arch. Okay, now so this is all about say analysis of arch and analysis of cables. Okay, so these are the analysis of arches and analysis of cable. Again, think again. Remember that some summary is there. So remember summary. Cables are always in axial tension. Whatever is it is, application of external loads are resisted by axial tension only in case of cable. Okay, flexibility, nature wise flexible in nature. Again, inextensible, whatever length is considered during application of load, it is constant. Okay, whole assembly of that cable is considered as a rigid. Okay, whole assembly means do that two supports in between this cable, it is considered whole assembly is considered as rigid support, rigid. Okay, And during analysis, cable is considered as flexible because after application or after consideration of flexibility or flexible in nature, we can there is a effect of temperature in the cable. Okay, so there is a different formulation also for the temperature effect also. Okay, so rise in temperature, what will be the effect of rise in temperature, what will be the effect on lower down the temperature. Okay, all this effect we can calculate on these cables. Okay, so again, after application of loads on the cable, all the low external load are neutralized by only the application of axial tension only. Okay, then in case of arches, after application of loads, whole assembly is neutralized by using horizontal thrust only. And the nature wise, if we think about nature about this arch, so it is always in axial compression. Okay, so it is again, I'm repeating that arches are opposite to cables. Cables are always in axial tension, whereas arches are always in compression, axial compression. Okay. Again, in the simple beam, simple horizontal beam, we can calculate the additional external forces by using shear force and bending moment values. Whereas in the arches, we can calculate the applied external forces by using horizontal thrust only. Okay, so in the case of simple horizontal beam, we calculate always we calculate simply shear force and bending moment value, support reaction, shear force, bending moment value. Draw the shear force diagram, draw the bending moment diagram, and solve that numerical. Calculate the nature of that application of forces, and we can calculate that reaction is in what extent that forces can be neutralized. Okay, but in case of arches, we calculate the support reaction. This parabolic arch, we in case of parabolic arch, we consider this parabolic arch just like a simply supported beam. Consider horizontal beam with number of forces applied on that arch. Okay, analyze as per that. Analyze means analyze in the sense calculate the support reaction regards to that horizontal beam. Okay, considering the horizontal beam. After calculation of these horizontal reactions, number of unknown reactions or additional number of forces are calculated using horizontal thrust only, by horizontal thrust only, that using that formulation of horizontal thrust only in case of arches. Okay, again, if we think about the classification, so there are basically in case of arch, there are funicular arch, parabolic arch, semicircular arch, we can say. Okay, so basically these three types of arches are there. In that, funicular arch is the one of the case. In case of funicular arch, it is a perfect case of axial compression. Okay, in parabolic arch, again in the analysis of parabolic arch, a parabolic arch is considered as a simply supported beam. It is considered as a simply supported beam, analyzed as a simply supported beam. Okay, again calculate the support reaction and calculate the neutralizing forces and moments in that. Okay, again in case of rib is considered no bending moment and shear force develop in that rib. Only horizontal thrust is developed in case of arches. Okay, then we have seen about some formulation regarding this UDL over the span, UDL over the half span, some concentrated load over the crown itself, and some concentrated load at a certain distance x from in left support or right support. Okay, so in that case, all this standard formulation is there. So for the 2-inch parabolic arch, it is we can use this formulation, standard formulation, to calculate horizontal thrust. Okay, again 3-inch parabolic arch, we can consider 3-inch parabolic arch is a statically determinate structure, whereas 2-inch parabolic arch it is statically indeterminate structure. Okay, now another we can consider, we will think about slope deflection method. Okay, it's the second last method, slope deflection method. Terminology of regarding slope deflection method, then by after terminology, there will be a simple numerical. We will solve that simple numerical and we'll discuss about the member forces, or whatever is the number of forces, number of external application of forces. Okay, all this parameter. After this, we will consider about moment distribution method, MDM method, one small numerical in that case, and we will solve that small numerical. Then we will stop. Okay. So first of all, we will take as slope deflection method. Okay. So method is used to analyze indeterminate structures. Basically, this method is used to analyze indeterminate structures. Now, indeterminate structure. Now the question comes in our mind: what kind of indeterminate structures? So, like continuous beams, plane frames. Okay. So for that continuous beams, plane frames, we specifically use this slope deflection analysis. Okay. Basic two unknowns are there. Slope is there at a particular joint or at a particular support, and displacement of a particular support or displacement at a particular joint. Okay. For this slope deflection method, we will not consider as a joint. We will consider as a support, or we use the terminology for a particular joint. This is a support. Okay. So at a particular support, we have to calculate, say, rotation for that support, and rotation of a member about that support, displacement of that particular member about any support. We have to calculate these two parameters, basic two parameters. Another name is that slope deflection method is also known as displacement method. Okay. And basically there are three basic application. That is, slope deflection method can be applied directly or indirectly in the MDM, means moment distribution method, Carney's method, and stiffness matrix method. Okay, like that. Again, it is used for indeterminate structure, analysis of indeterminate structure like continuous beams, frames, plane frames, etc. There are two basic unknowns we have to find, that is support rotation at support, and support displacement. Okay. Another, it is termed as displacement method again, and application in MDM, Carney's method, and stiffness matrix method. Okay. So method establishes the relation between the degree of freedom, that is displacement and rotation, and member end moments. So this is a method which develops or establish a relation between, say, degrees of freedom for a particular support or particular joint, and for that particular, or we can say a particular member, and the for member end forces or member end moments for that particular member. Okay. So this relationship, develop relationship, is called as slope deflection relationship. Okay. So step by step procedure, consider all joints to be fixed. Okay. Now, if we think about the continuous beam, first of all, if we think about the continuous beam, now in the continuous beam, sometimes it may happen that some support is fixed, some support is hinged, and some support we can say free. Okay. But if we have a beam which have, say, a continuous beam, means more than two supports, we can say. Okay. So simple continuous beam which have, we can say, three supports. Okay. So two members are there, A, B, C, in which we can consider joint A will be rigid, or we can say joint A will be fixed, joint B will be hinged, and joint C will be hinged, like that. But when we'll consider that continuous beam for the analysis of this by using the slope deflection method, we will consider this, all these supports are fixed supports. So consider all the joints or supports are to be fixed. Okay. Then determine fixed moments for the particular member. Now, if I consider these two, if I consider this two uh, members, say this A, B, and C. So we have to consider this is fixed, and this is fixed. Means ultimately this member AB is fixed at A, this member is fixed at B. Again, this in case of this member BC, it is fixed at B and it is fixed at C. Okay. So we have to consider, but ultimately, practically, this is not the case. We have considered that A is fixed, so joint A is fixed, joint B is hinge, and joint C is hinge. Okay, but it is a step-by-step procedure. We can say, just like assumptions in the analysis, in any analysis. So, like during analysis of this, by using this slope deflection method, we can say this is the assumptions. Okay, so by using this assumption, we have to move further. Okay, so determine member end forces. So MFAB, it is a general notation of to show fixed end moment. So F stands for fixed. So fixed end moments. So M stands for moment. So fixed end moment about AB and fixed end moment about BA. So we have to calculate about these two fixed end moments. So again, we have already considered that positive moments are clockwise moments and negative moments are anti-clockwise moments. Okay, like so, then allow support B to settle with respect to support A. Okay, so establish a relationship between these two supports. So support B we have to settle, allow to settle in the downward direction, and derive this relation. Okay, derive this relation. I have not considered this relationship means derivation for relationship. Okay, I have shown directly whatever is the final output of this. So after considering this whole assembly, so whatever is the fixed end moment, so member end moments are 6 EI delta by L square. And again, now both ends are fixed. We have considered both ends are fixed, and this is assumption. This is the assumed parameter. Means if I consider this is a joint as a fixed, so this displacement can't be possible, है ना? So this is assumption. On this assumption that both ends are fixed, but we have considered that support B settling down. So by doing this, by considering this assumption, so there will be these member end moments will be like this. So because this there is a no load is there and both end is fixed, so means symmetry is there, similarity is there. So that's why this member end moments is similar. So 6 EI delta by L square and 6 EI by delta by del L square. So member end moments will be like this. Okay. Now support A allow support A to rotate. Okay. Now support A allow support A to rotate about support B. So with respect to B, no. So in that case, so another again the member end moments are calculated by using these relations. So it is derived relation. So there is a derivation in the available in the different books. So you can refer different books for the these derivations. Okay. So by taking this assumption, we can calculate this rotation. So member in after application of this rotation, so member in moments will be 4 EI theta A by L, whereas 2 EI by theta A by L. See, in this case, these two parameters are similar, but in this case, these two parameters are not simple. Sorry, similar, because if I consider rotation about this, so I have to consider this is the hinge joint, because in fixed joint rotation is not possible. Okay, so if I have to consider rotation at joint A, in that case I have to consider this joint A is hinged, means this vertical and horizontal movement is not possible, it is restricted, but rotation is possible. Okay, so in that case, so for the hinge joint to near the hinge joint, the member end moment will be 4 EI theta A by L, whereas in terms of theta A, because we have allowing only support A to rotate, we are not allowing support B to rotate, means at support B we have the relation in terms of theta A only, we have not relation about theta B. Don't confuse in that, means many students will go that at support A will be 4 EI theta A by L and at support B will be 2 EI theta B by L. Not that not the case, means whatever is the rotation is allow at support A, whatever is the effect in terms of moment at support A will be the 4 EI theta A by L, and uh, and, and the reaction or whatever is the uh, we can say effect of this rotation over this joint B will be 2a theta A by L. So that's why this both relations are in terms of theta A only, because we are allowing only support A to rotate. Okay, if I allow support B to rotate about A, then in that case this will be 2ei theta B by L, and this will be 4 EI theta B about upon L. So in that case, if I allow support B to rotate, so in that case only we have this 4 EI by 4 EI theta B by L will be on right hand side, and 2 EI theta B by L will be on left hand side. But when When case will be the when we allow when I allow support B to rotate about support A. Okay, in that case only theta B will come into picture. Remember, okay, don't confuse in between these two parameters. Okay, now so allow support B to rotate similarly. So this will be for support A and this will be for support B. So again similar to that. So 4 ER theta B by L and 2 ER by theta B by L. So again like this. Okay, considering joint hinge here and considering joint fixed here and derive the relation for the member and moments. Okay, so these are the relation for M. Okay, now axial deformation is neglected and shear deformation is neglected. Okay, means whatever is the this beam means whatever is the shear deformation is neglected and axial deformation is neglected for a particular member. Okay, this is the assumption. Another basic assumption for the in the analysis during this uh, by slope deflection method. Okay, now when both ends are fixed, we can say because it is a basic assumption, that is we have to assume all the joints are fixed. So again in behind this relation there is a derivation. Behind this relation this is a derivation. So basically what is the derivation? See, now MAB is nothing but the all the moment, we can say fixed end moment, say FEM plus say member end moments. Okay, so we have calculated till now. See, this M is equal to now FEM plus MEM, fixed end moments plus member end moments. Now, member end moment we have find two in the two types. Okay, by using displacement and by using rotation. Okay, so ultimately all the moment for a particular joint will be summation of all these parameters. Right. Now, fixed end moment for a particular member about that joint and member end moments for a particular member about that joint in terms of two parameters, that is displacement, vertical displacement and rotation. Okay, so like see, if I consider MAB means moment in member AB means what? Fixed end moment in member AB as well as all this term will be MEM in terms of these two parameters, right? Now, if I consider this AB, beam AB, so there will be what? So MAB means what? What parameter will come into picture? Now, so this, first of all, we will think about displacement. Okay, friction moment, we have MFAB. Notation is FFAB. Okay, and whole this term is will be MEM. Okay, so for MEM, what will be the A for AB? What will be the value for displacement? Okay, so for considering displacement, there will be a value of 6 year delta by L square. But 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 displacement is considered in the downward direction, vertical downward direction. So this value will always be negative. This value will always be negative because we are considering again no, simple rule. Positive vertical upward force is positive and upward downward force is negative. Okay, similarly downward movement is negative, upward movement is positive. Okay, just like this moment, again clockwise moment is positive, anti-clockwise moment is negative. Again, to neutralize these, there will be development of anti-clockwise moment. So anti-clockwise moment is negative, so that's why it is negative in nature. Simple. Okay, so that's why it is this parameter will be what? This parameter will be 6 EI delta by L square. So 6 EI delta by L square, again negative. Okay, so this will be in terms of delta. Hmm. now now in case of theta we have to find, so in case of theta at joint we have thinking about member AB. So first of all, we have this A and we have this B. Okay. So at A there will be relation as 4 ei theta A by L. 4 ei theta A by L. So 4 ei theta A by L. My mouse is not working. So 4 ei theta A by L. So this relation is comes here. So 4 ei theta A by L. Okay. Now, so 4 ei theta A by L. So theta A by L. Okay. So 4 ei by theta A by L, and at B will be what? For this means joint A is allowed to rotate. So 2 ei theta A by L. So 2 ei theta A by L. But what? But what? But here is theta B. Here theta B. So theta B. What will be the value of theta B? So what will be the value of theta B? So what value of theta B will be 2 ei theta B by L. Okay. So these are the three basic parameter, and after assembling these three parameter in this equation, so 4 ei theta A by L so will be this, 2 ei theta B by L will be this, and minus 6 ei delta by L square will be this. And from this bracket, if I taken out 2 ei by L outside, so we have only 2 theta A plus theta B minus 3 delta L. Okay, so this is the simplified relation. Okay, similarly for BA, so BA will be 2 theta B, 2 theta B and theta A minus 3 delta by L, like that. Okay, so like this. Okay, so this is again membrane force, and this is the simplification form in case of AB and BA. Okay, by using these two equations, we can calculate moment and final end moments. Okay, now this will be again simplify when we calculate these. We can calculate or we can solve a numerical problem. Okay, then, then now now friction moments. These are the common. Maybe in this during the third semester, we will thinking about this friction moment or studied about friction moment. It is a constant values and constant formulation. Means these both ends are fixed and one concentrated load acting at a half of distance. So in that case, MFAB is equal to WL by 8 and WL by 8. Similarly, if UDL is there, this is the UDL W in this case, and the UDL W. So in that case, fixed moment will be WL square by 12. It is like this. If concentrated load acting here, concentrated load was at the center, that L by 2, L by 2. But whereas this concentrated load is at distance A from left hand and distance B from right hand. So in that case, so fixed moment will be WB square by WB square A by L square and WA square B by L square. Okay, like this. So next, MFAB will be 5W if triangular load is there for a fixed moment. So fixed moment for triangular load is there 5W L square by 96. So like this. If moment is there at the center at a distance L by 2, L by 2. So MFAB will be M0. It is denoted by M naught or M to the suffix 0 or O. It is M by 4, M by 4. Okay. Then similarly, if a fixed beam with half UDL over L by 2 distance from left support. So in that case, MFAB calculated by using this. So MFAB, it is 11WL square by 192, and 5W and MBA will be 5WL square by 192. Okay. So this is a simple numerical. Let us solve this simple numerical. Okay. So we have again. So we have again this support A is fixed. Support B it is hinged. Support C it is hinged. Okay. And now over this joint, over this beam AB, there is a UDL load, UDL of 3 kilonewton per meter. And over this beam BC, there is a concentrated load at the center at 4 meter, 4 meter. And the length of AB is 20 meters. Okay. So step one, we have to consider all the joints are fixed. Step one, simple. We have to consider all the joints are fixed, but practically it is not fixed. It is we can say it is. We can see here with fixed. It is fixed. It is hinge. It is hinge. Okay, but it is practically it is hinge. It is hinge at B and C and at fixed at A. But whereas we have to consider for this analysis procedure wise, it is fixed. So fixing joint A and joint B. So joint A and joint B with a UDL of 3 kilonewton per meter over that for a span of 20 meters. So calculate by using WL square by 12. So calculate this friction moment. Again, anti-clockwise moment. So minus sign is there. Okay. So minus 100 kilonewton meter will be the friction moment at for MFAB. Then MFBA, again, it is a clockwise moment. So WL square by 12, it is plus 100 kilonewton meter. Okay. So MFBC, again, a single point load at the center, 4 meter distance. So MFBC will be WL by 8, so minus 10 and plus 10. Right. This is this moment is anti-clockwise, so minus 10 is there, and this moment is clockwise, so plus 10 is there. Okay. So these are the fixed moment. Again, these diagrams are known as FBDs. So this is a FBD of beam AB, and this is a FBD of beam BC. Okay. So it is a free body diagram of AB and free body diagram of BC. It is drawn considering this all the joints are fixed, but in the practical case it is not fixed. Okay. Now, so this is the basic equation we have. This is the basic equation we have, and by using this basic equation we have to calculate these final end moments. Okay, final moments at support. So for this beam, given loading condition, we have calculated fixed moments. Okay. Now, so slope deflection equations for that particular beam AB and BC will be like, so MAB will be the final end moment. So MAB will be the final end moment, and MFAB will be the fixed end moment for beam AB. And this again, this is a fixed end moment. So this is fixed end moment, and this is member end moment. Okay. So now, so MAB will be again MFAB will be minus 100, MFAB is minus 100, so minus 100, and 2 EI by L, so L is 20. Okay, so 20. So again 2 theta A of simplification, this same equation, 2 theta A plus theta B minus 3 delta by L. Okay, now in this case, see, only this is 0, this is 0, only theta B is present. Why? Okay, now in this case, theta A, theta B, and delta. Okay. In general case, this equation suggested this this is a general equation. This is a general equation. We have not known about this joint A is fixed or hinge. Okay. If it is hinged, means rotation is possible, means theta value is possible. But if the joint is fixed, means if the joint is fixed, means horizontal vertical movement is not possible, as as well as rotation is not possible. Okay. But whereas if we consider this problem figure, so at joint A, it is we have considered as fixed support, means it is given as fixed support. So that's why rotation at A is not possible because of fixed support. So that's why theta A value is 0. Okay. And in the problem figure, at B it is a hinge joint. At hinge joint means what? Displacement in the vertical and horizontal direction is restricted, whereas rotation at B is possible. Means rotation is possible. Practically, rotation is possible at joint B as well as at joint C. It is a both joints are hinged, both supports are hinged. So that's why rotation is possible. But whereas vertical and horizontal movement is not possible. Okay. So for both the cases, theta B, theta A will be 0. Theta B is exist. Rotation is possible at joint B. Okay. Delta is not 0. Delta is not possible. Again, joint A is fixed, so delta is not possible. Okay. So that's why delta is 0. So only is MAB will be minus 100 plus 2 EI by 20 into theta B will be the final equation. Okay. Similarly, if we think about MBA, okay. Now, in case of MBA, if we think about fixed moment, it is plus 100. Again, 2 EI by delta, sorry, 2 EI by L, that is 2 EI by 20. Again, theta will be 0, fixed end. 2 theta v will be there, and again delta will be 0. Okay, because we have considered that we have taken assumption that not assumption, we can see we can consider that joint A is given as fixed, joint B is given as hinged. For both the joints, we can have this knowledge that for both the joint, vertical displacement is not possible. Okay, so only for the joint B and C, only rotation is possible. For the joint B, for the joint A, as well as for the joint C, horizontal and vertical movement is not possible. So that's why delta value is 0 for BA also. Okay, then this is for beam AB and BA. Okay, now similarly for BC and CB. So for BC and CB, so again MFBC 2 EI by L and this equation. Okay, so again MFBC is calculated as minus 10. So MFBC is calculated at minus 10. So minus 10. So minus 10. This equation again, rotation at B, rotation at C is possible. That's why these two terms are present. Okay, whereas displacement is not possible. Again, hinge support is there, so displacement is not practical. So displacement value is 0. Okay. Again MCB. In case of MCB, again fixed moment, that is plus 10. So it is plus 10. So it is plus 10 value. Okay. Again this equation. Again these two values are possible. Rotation at B and C is possible. Displacement at displacement at displacement for the particular beam is not possible. So it is 0. Again, think about this. Okay, we have given with this joint A was fixed, joint B was hinged, and joint C was hinged. But for the three joints or three supports, vertical and horizontal displacement is not possible. For A, rotation is not possible. For B, rotation is possible. For C, rotation is possible. Okay, means basic two unknowns are there, that is theta B and theta C. Okay, so only basic two unknowns are there, which means if I ask the question that analyze this beam, if I ask the question analyze this beam by using slope deflection method, so we should know that for what we have to calculate or for what we have to analyze this beam. Okay, so for that particular beam, we have these two basic unknowns, and for these two basic unknowns, we have to calculate or we have to analyze this beam. Okay, so for that we have calculated these fixed end moments and this relation. This is the general relation. By substituting the values, actual values in this general relation, will give the final unknown reactions. Okay, or we can say unknown forces. So these unknown deflections are only two. That's why I have not suggested in the previous uh, means at the starting of our numerical. Uh, I have explained first. I have explained this whole formulation. Then I am going towards these basic unknowns. So basic unknowns are these theta b and theta c. Okay. So for what this is a basic unknown. Now these are the equations. These are the basic friction moment. These are okay. Up till now this is okay. But after doing this, how can we solve this for theta b and theta c? Now we have four equations that two equations are for theta b and two equations are for theta c and theta b. Okay. So now how can I solve these four equations? After solving these four equations, we can calculate theta b and theta c value. Okay, but for the calculation of these for the calculation of these two unknowns, we should have some relation for, because two unknown four equations. I it is not possible to calculate these two basic unknowns. Okay, so now some basic equations can be now. Just look after this problem figure. Now joint A is fixed. Joint A fixed means what? Restriction towards what? Restriction towards about three parameters: vertical reaction, horizontal reaction, as well as rotation. Okay. Restriction to rotation is there means what? Moment is present there. Means moment value will be come there. Moment value will come there. Okay. Definitely, when restriction to moment is there, see, restriction to upward movement, restriction to horizontal movement is there, means horizontal and vertical reactions are there, right? If restriction to rotation is there, means moment is there. 100% sure shot. If restriction to rotation is there, moment is present there. Okay, but if it is free to rotate, if it is free to rotate, in that case, moment will not comes into picture. 100% every time when rotation is possible, there will not be any reaction in terms of rotation. Okay, because it is free to move. It is free to move in the or free to move in the clockwise or anti-clockwise direction. So at joint B and at joint C, there will be rotation possible because these two joints are hinged. At hinge joint or at hinge support, rotation is possible. So that's why rotation is possible, but moment is not possible. Means what? Rotation is possible means moment is zero. Okay. So what can be the compatibility equation? We can say, so moment at B will be equal to zero. Moment at C equal to zero. Okay. Now, moment at B equal to 0, moment at C equal to 0. Now, these are the in case of support or joint, but we have to give this relation in terms of members. Means at joint B, there are two members, a BA and BC. BA and BC. There are two members. Means what? If at joint B moment is 0, means what? Means what? Moment moment at BA plus moment at BC will be equal to 0. Moment at BA plus moment in terms of BC, moment in terms of BA plus moment in terms of BC will be equal to 0. This will be my first equation. And second equation will be what? If I consider joint C, at joint C, moment is 0. At joint C, moment is 0. So in case of this, so contribution of this joint moment over this member BC will be MCB equal to 0. So there are two basic equations are there. That is two for this two basic unknowns. Equilibrium equations needed are this MBA plus MBC equal to 0 and MCB equal to 0. Now by using these two equations, I can solve for this theta B and theta C. Now, by using these two equilibrium equations, I can calculate this theta B and theta C. So by substituting all the values in this equation, simple, okay, all the values in this simple, okay. Now, all the time, see, remember one thing, all the time this equilibrium equation will change, okay. This is standard. This formulation is standard. This formulation is always standard. Okay, this formulation for MAB and this formulation for MBA, MBC or MCB. Okay, notation will change, but nature of this equation will remain same all the time. Okay, all the time this will be positive, this will be positive, this will be negative. All the time this nature is always same, similar. Okay, for all the numerical, but only difference is that depending upon this loading condition and supporting condition, these zero, this rotation, this displacement, all this value will change. Okay, so remember that these equation is constant for the different numericals for different members, but this equilibrium equation, remember this equilibrium equation, this will change numerical to numerical. This will not constant. Okay, this will change depending upon the support reactions. This will change depending upon the support conditions. Okay, if delta, if hinge support is there, in that case only, so moment will be equal to 0 because free rotation is possible. If fixed support is given, then moment is present in that case. So rotation is not possible, means theta equal to 0. Okay, so moment is possible. So that's why in the equilibrium equation, moment at A or moment at AB equal to 0, it is not possible. Okay, that's why we have considered only the joint B and joint C. So that's why MBA plus MBC will be 0. So contribution of this moment over this joint B will be in terms of BA and in terms of BC. So contribution of this whole moment in BA and BC will be MBA plus MBC will be equal to 0. Okay. Ultimately, moment about B will be equal to 0. Okay. Similarly, moment about C. So moment about C will be equal to 0. Okay. So contribution of this moment about C equal to 0 will be in CB, in CB, right? So by doing this, by considering this, so we have this um, theta b value, and we have this value of theta c. Okay, like that. So by doing this, we have calculated theta b in terms of EI. We have value of theta. We have value of theta b, and in terms of EI, we have value of theta c. Now back substitution, substitute back in that equation. So these are basic equation. So this equation, we can say this is 2, this is 3, and this is 4. So these 4 equation back substitute that values of theta b and theta c in these equations. Or we can say we have these equations, say A, and this equation is B. If we by solving this AB, we will get theta b and theta c. Okay. So final moments will be C again. MAB. Sorry, MAB means it is a contribution of moment at A in member AB. It is a contribution of moment at A in member AB will be this 114.78 kilonewton meter. Again, nature wise it is anti-clockwise, so it is minus. Okay. MBA again, so substitute the values theta b, so it is theta b, so it is 170 is 147.82 and 53.91, so 147.83. Okay, so nearby it is 82, 83. Okay, so MBA will be 70.44, and we have this. See, look, we have considered here moment about B equal to 0. Moment about B equal to 0 means after analysis, whatever moment at B we will get should be equal to 0, right? So these value MBA plus BC will be equal to 0. So this is a plus 70.44 kilonewton meter. So this is minus 70.44, so it is 0. So means all the calculation we have calculated, it is okay, it is fine. Okay. So this all formulation gives the right way, or we can say after doing this analysis, we can consider that my numerical solved numerical is okay. Okay. If this MBA was different, means 70.44, and MBC is says 65 point something, if happens, so it is definitely there is some problem in formulation or your calculation or calculated method something, or during calculation of theta b and theta c, these values may be some wrongly calculated. This prediction is that. Okay, so be careful regarding calculation of theta b and theta c, because all the calculations are dependent on this theta b and theta c. Okay, so by after substituting this, so this 70.44 and 70.44 is just counteract, so counterbalance it, so it is 0. So ultimately MBA and MBC it is 0. Okay, ultimately MCB again it is comes out to be 0. It is MCB is again comes out to be 0, right? So this is a simple numerical. So it is a continuous beam problem. It is a continuous beam problem with two beam, okay, 3 supports, whereas one support is fixed, 2 supports are hinged. We have calculated 2 unknowns, that is rotation at B, rotation at C. So these are these 3. These are the continuous beam problem. Simple continuous problem we have solved, and we have verified also that solution we have calculated, it is fine, it is okay, it is true. Okay, next. Next, it is the last method. Now we will consider about the moment distribution method. Last method, it is again its terminology. Again terminology, and after terminology, one simple numerical, and after simple numerical, we will stop. Okay. So again, suitable for analysis of continuous beam and frames. It is just similar to that. And again, we can say some of the portion, some of the basic portion are similar to that of slope deflection method. Okay, method presented by Hardy Cross by of USA in 1929. Again, it is also known as displacement method of analysis. Slope deflection method is also not termed as displacement method of analysis. Okay, it is an indirect method. We can say indirect method to solve equilibrium equations, and it is an iterative process. And also, it is also known as relaxation method. Another term is that relaxation method. Okay. So if we calculate fixed moment, see in during this calculation, in the slope deflection method, if we think about calculation or methodology, we have calculated fixed moments. Then after fixed moment, we have calculated the member end moments depending upon this rotation and rotation as well as displacement, vertical downward displacement. Over this, we have derived this formulation. Okay, but in case of MDM, we have this stiffness parameter as well as distribution factor parameter as well as carryover factor. Okay, so different methodology depending upon different methods are there. So in case of slope deflection method, we found the relationship between these deflection friction moments as means we have found the relation between friction moments and member end moments in terms of displacement and rotation. Okay, but in case of MDM, which is indirect method of analysis, in case of the in this case we calculate final end moments by calculating fixed end moments, stiffness for a particular member, then distribution factor depending upon that stiffnesses, and carryover factors. Okay, now what is this carryover factor? What is this stiffness for a particular member? We will see. Okay, so if both ends are fixed, or we can say far end is fixed, so stiffness for a particular member is calculated by 4 EI by L. Okay. Again, derivation is available in number of textbooks. You can refer that number of textbook for this derivation. Okay. Now directly formulation, I have given this formulation that if far end is fixed, so in that case stiffness for a particular member is calculated by 4 EI by L. Okay. Again, far end is hinged, so stiffness is calculated by using 3 EI by L. Okay. Now, by doing this means if far end is fixed, means we can say both ends are fixed. In this case, stiffness of a member is calculated by using 4 EI by L. Okay. If one end is fixed, another end is hinged, in that case, stiffness of a member is calculated by using 3 EI by L. Okay. Joint stiffness, just similar to equilibrium equation, when we calculate the member moment at a particular support or joint and contribution of that moment over that particular members. Okay, just similar to that, joint stiffness for a particular joint will be common stiffness or compound stiffness. We can say compound stiffness for a particular joint will be, say, K1 means K for the previous beam and K for the next beam. Like if two beams are connected, if four beams are connected, like for a particular beam, and in case of a plane frame, say a node or a joint is there and four members are connected, in that case the compound stiffness or joint stiffness factor will be K will be equal to K1 plus K2 plus K3 plus K4, like that. So at a particular joint, number of members are connected will be the addition for a particular members will be the compound or joint member stiffness. Then carryover factor. Carrier factor is that if I have considered a joint B, okay, if I have considered joint B, see, in this case, right, sorry, in this case, if I consider joint B, I have considered joint B I have doing calculation for joint B. I have calculated moment at joint B, and joint A is hinged, joint A is fixed, joint C is hinged. Okay. When if I doing calculation for moment at a joint B, when I am doing the calculation for a moment at joint B, and I have to distribute this moment at joint A and joint C. Okay. So in that case, if joint A is fixed, then there will be a carryover factor of this moment. This carryover factor will be, if suppose moment at joint B will be MB, so in that case at carryover factor at joint A will be MB by 2. Okay, whereas this MB will distribution of this MB or carryover factor or carryover of this MB over this joint C will be 0. Okay, so because this is hinge again, terminology is same. Fixed, it is fixed, that's why here is moment, means whatever is the moment present here, the effect will be transferred towards the fixed support. But whereas this hinge support is there, again rotation is possible, moment is not possible. At hinge support moment is 0, so that's why it is 0. So that's why carrier factor will not be in case of hinge support, right? So whatever moment is present here will be nullified or will be balanced by taking half of its effect over the fixed support and 0 effect towards the hinge support. Okay, remember that. Okay. So carrier factor. So again, if I consider for joint A and joint B is fixed, so carrier factor. Sorry, this is the factor. This is a factor, not further. It is a factor. So carrier factor fixed further fixed end over the farther fixed end. Sorry, it is okay. It is at farther fixed end. So it is a and this is a farther fixed end. So it is m by 2. And if it is a hinge, so it is a 0. Okay. Now, example. Simple example. Calculate distribution factor for a beam AB using figure shown. Okay. So this is a figure. This is a, we can say, a plane frame. Okay. In a one plane. Okay. So joint A, joint B, C, D, and E. Okay. So whereas out of these 4 joints or out of these 4 supports, 3 supports ADC, these 3 supports are fixed, whereas support E is hinged. Okay. Now we have to calculate this, first of all, joint stiffness for joint B. Okay. Now for joint B, we will consider members. So there are 4 members are there. This is BA, BD, BC, BE. Okay. Now we have seen if this member, this is pinly connected, okay, pin jointed connected, but for the timing we will assume that this joint B will fixed. Okay. So this is fixed. This is fixed. So my stiffness factor will be 4 EI by L. So for BA, it will be 4 EI by L. So 4 EI by 2L. Now L is 2L. So 4 EI by 2L, it is 2 EI by L. Okay. Now, secondly, BC. Now BC, again, this is fixed. This is fixed. Again 4 EI by L. Similarly 4 EI by L. Again 3L. L value is 3L. So 4 EI by 3L. Right? Now, so BD. Now BD, again, this is fixed. This is fixed. So again 4 EI by L. So 4 EI by, this L value is 4L. So 4 EI by 4L. So EI by L. So EI by L will be the stiffness factor here. Okay. And similarly for BE, now for BE at joint B, it is fixed. At joint B, it is fixed. But whereas at joint E, it is hinged. So 3 EI by L, it is 3 EI by L. So that's why L value is 4L. So 3 EI by 4L will be the 3 EI by the 4L will be the final value. Okay. So this will be the stiffness factor. Okay. Now joint stiffness, total stiffness at the joint B, total stiffness at joint B. So K value will be equal to what? So EI by L. Again, EI by L will be the common, and all this 2 plus 4 by 3 plus 1 plus 3 by 4 will be the factors. Okay. So by doing this, we will have this 61 by 12 EI by L. So this is a total. Okay. Again, this is a joint B connected with the four members, so that's why the joint total stiffness at joint B will be the K1 plus K2 plus K3 plus K4. So like this, we have calculated this joint stiffness at B. Okay. Now, calculation of distribution factor. Now, distribution factor is nothing but this particular member stiffness is KBA divided by total stiffness factor. Okay, means KBA divided by capital K. So similarly, 2 EI by L divided by 61 by 12 EI by L. So 0.39. Similarly for BC, for 226, for BD, for BE, like this, for 15, like this. Okay. So calculation of this DF. So for calculation distribution factor for AB using this figure shown. So target was we have to calculate this 0.39, but for the timing or for the simplicity or for the understanding point of view, I have considered these four members and calculated distribution factor for all the members. Okay, so these are all the values of distribution factor for all the members. Okay, next. So now, now a simple numerical, a compound beam or continuous beam we can have. Whereas joint A, again joint A is fixed, joint A is fixed, joint B is hinged, joint C is fixed. Okay, and we have this value IAB and IBC. We don't have the value of E. Don't have the value of E here. Okay, length value is given 20 meter, 20 meter. Okay, and on BC there is a UDL. It is 200 kilonewton per meter. Okay, now calculate member stiffness. Okay, so for again BA and BC, there are two members. Okay, so 4 EI by L. Again, this joint B is hinged, but if orientation wise, if we think about, so joint A is fixed, joint B will also be fixed, and joint C will also be fixed. Okay, so 4 EI by L, 4 EI by L, and 4 EI by L for B and BC. Okay, so substitute all the values. Okay, L is 20, 20 is same. Okay, 4 EI by I value is substituted and L value is substituted. E value is not substituted. Okay. So by doing this, total stiffness is addition of these two parameter. This two parameter will be addition of these two parameter. So total stiffness will be this at joint B. Okay. Similarly, distribution factor will be this BA KBA divided by this K. Okay. So again, this will be 0.33 and KBC upon K will be this 0.67. Right. So these are the distribution factors. Now, if moment is applied at joint B, right? Now, what distribution factor shows? Okay, just remember what this distribution factor shows. Now, if I consider this joint B, and if a moment is acting at joint B, if this moment is acting at joint B, means that 0.33 with 33% contribution towards this beam BA and 67% contribution towards this beam BC. Okay, means whatever whatever moment is there at B, just remember whatever moment at B, okay, the contribution of that moment will be 33% towards AB, member AB, and 67% towards BC. This is the meaning of this. Okay, this is the meaning of this. But whereas at joint B, we have considered here both ends are fixed, but practically in the problem figure, joint B is hinged. Okay, this moment is not present there. Rotation is possible, but moment is not present there. Mean whatever is the moment coming over that joint B, we have to nullify that moment. Okay, whatever is the moment coming over that joint B, we have to nullify that moment. Okay, so we have this. So see, so calculate, first of all, calculate friction moment. Calculate friction moment. So for AB, there is no load, so friction moment will be 0. And for BC, there is a 200 kilonewton per meter, so it is a UDL. So we will calculate 200 into L square by 12. So calculate this friction moment. So at B for a BC, it is a friction moment is minus 6666.67, and for CB it is plus 6666.67. Okay, kilonewton meter. So these are the fixed moments. So we have distribution factors. Okay, now we have this minus 60 minus 6666.67. This value will be distributed according to these distribution factors over this beam AB and over this beam BC. So next, so in reality, so again joint B is assumed, only assumed that it is fixed, only assume that fixed, but in reality it is not fixed, it is hinged. So that's why it is a moment is zero. So it is unbalanced moment. We can say it is minus 66.67. It is unbalanced moment. Okay. So first of all, we have to balance that moment. Okay. So in reality, what will be the equation of equilibrium? Right, MBA plus MBC equal to 0. Just like the slope deflection equation. What is the equilibrium equation? MBA plus MBC equal to 0. And to balance this, we will consider, we will not consider, we will have this, or we will require this plus 4 times 6.67 kilonewton meter value. Okay, now this plus 4 times 6.67 value will be distributed over these two beams by considering this distribution factor and carrier moment. Okay, so final moment. Okay, so this is joint A, this is joint A, this is joint B, and this is joint C. So this is the distribution factor we have calculated. Okay, so this is the friction moment, it is a minus value, and this is the plus value. So for to neglify this, we will have this value plus 66 here. Okay, so this value will be here. Okay, so now this value will be distributed over these two beams. So plus 66.67 into this 0.33, this value will be this. Okay, and this value 66.67 into 0.67 will be value will be like this. Okay, now again we have seen that if further joint is fixed, then carryover moment will be half of the moment will be transferred on the fixed support. But if the further joint is hinged, then half of the moment will not be transferred, it will be 0. Okay, so that's why further end was fixed. Further end, this end is fixed. Again, end C is fixed, means at both end this moment will be carried over. Okay, so that's why this 2200 will be halfly carry over by this joint A. So it is 1100, and this 4466.67 it is halfly carry over here. So that's why it is plus 2233.34. Okay, so finally just submit all the moments, submit and calculate the final moment. So 0 0 1100. So finally is plus 1100. Here it is 2200. Here this is difference of this, only difference of this. So minus 2200. So it is 0. So it is nullified. Okay. So our calculation is okay. Okay. And at joint C again it is not hinged. It is fixed. That's why. So moment is there. Moment is present. So 8900.01 kilonewton meter will be the moment present at joint C. Okay, so these will be the final end moments. Okay, so this is the simple numerical by using this moment distribution method. Okay, another numerical we can solve, frame numerical we can solve by this moment distribution method, slope deflection method. Okay, so this is a very first lecture over this MDM, over this slope deflection method. So that's why I have taken this continuous beam, simple continuous beam having two members, three supports. So we have analyzed one beam, continuous beam with slope deflection equation as well as MDM. So it is thank you for thanks for giving me opportunity for to give such a lecture. So on this useful techniques to analyze indeterminate structures. And thank you, Tulsiramji Gaikwad Patil College of Engineering. I thank the coordinators for the particular scheme, and I thank Department of Civil Engineering, Tulsiramji Gaikwad Patil Engineering College, to give me the golden opportunity to serve, like to teach on this particular subject. I am very thankful. Thank you.
Thank you very much, sir, for taking such wonderful lecture on structural analysis, and I assure that the student will definitely will get the benefit from your lecture, sir. Thank you very much for joining and delivering such a wonderful lecture, sir, once again. And now I open this session for question answer session.
Okay.
If any question from student side, please. Okay.
Okay.
Okay. Thank you, sir. Thank you for joining.
Okay. Thank you. Thank you.
Thank you, sir.